Welcome back. This is another one in the series of the primitives of harness engineering. And today the primitive is context management. If you've watched the earlier deep dives, you know the frame. The model is only one piece, and most of what makes an agent reliable lives in the harness around it. Context management is the piece that decides what actually reaches the model on any given turn. The window is finite, and protecting that finite attention is this primitive's whole job. I'm going to do this the way I like to, with one real bug carried the whole way through, so that the ideas stay concrete instead of abstract. Let me start with something that actually happened on a long session because it is the failure I want to explain. I had an agent working on a StreamIt bug. StreamIt is a little app I run that broadcasts a live cricket match to YouTube straight from a phone. The phone sends video over WebRTC. A node server re-encodes it with FFmpeg and pushes it to YouTube. The complaint on this ticket was that on a real cellular connection, the video went choppy and low resolution, and the audio came out garbled, almost noise-like. The bug report linked out to a pile of stuff. The server's Docker logs, an earlier session where we had already worked the video side, and a design document from the pipeline work that I had done. And the agent started out well. It read the ticket, opened the encoder code, pulled the logs, and started forming a theory about the FFmpeg encoder restarting over and over. Then, maybe around 40 turns in, it started acting weird. It reopened a file it had already edited and asked what was in it. You can see the thinking, and it was thinking along those lines. It proposed a fix it had ruled out a few turns earlier. At one point, it contradicted a decision that we had made together, like the first half of the conversation had quietly fallen out of its head. And here is the part I want you to sit with. The model did not get worse. Same model, same weights, same settings. What changed is what was in front of it. The window had filled up with logs, half-read files, and tool outputs, and the stuff that actually mattered got crowded out. That is a context management failure. When people describe this, they usually say something like the prompt got too long or it lost the thread. I think it helps to be more precise because the fixes are different depending on what actually went wrong. Drew Brunig, and I might not be saying the name correctly, has a breakdown of how long contexts go bad that I keep coming back to. And there are names that are worth borrowing. One is poisoning, which is a wrong fact or a bad tool result gets into the context and then keeps getting referenced as if it were true. Second is distraction. The context gets so long, the model over focuses on it and leans on what is in the window instead of what it actually learned in training. Third is confusion. Superfluous material is in the context, and the model uses it to produce a much worse answer. And fourth is clash. The context accumulates facts or tool results that contradict each other, and that internal conflicts ends up degrading the reasoning. So in the StreamIt session, I had at least two of these. There was distraction because the Docker log ran thousands of lines and ate most of the window. And there was clash because the design document described the pipeline as already normalizing every frame to a constant 1080p, which is the fix we were aiming at. But the deployed code did not do that yet. Document and reality disagreed, and the agent trusted the document. So when I say protect the model's attention, this is the exact thing I mean. So keep these four from happening is what we should be trying to focus on. In the harness engineering deep dive, I said this out as primitive 3 in a stack of 10. Context management sits right after context delivery and right before the tool layer. The way I framed it there still holds. The job is to decide what enters the model right now. Retrieval, ranking, summarization, compaction, context assembly. The names on the tools change, the job does not. I want to draw one boundary upfront because this primitive gets blurred with two of its neighbors. It is not RAG. Dheeraj covered retrieval augmented generation in his deep dive. And that is the layer that asks what knowledge exists that could be pulled in. Context management is the next decision of all the things we could pull in, what actually goes into this prompt on this turn. It is also not memory. We did a whole deep dive on memory, and that is about what survives between runs. Context management is narrower and more immediate. It is about this window right now. I keep them separate in my head like this. Delivery is what is reachable, memory is what sticks around, context management is what makes it onto the desk in front of the model for the current turn. Start with the simplest thing that could work because it is what most early agents actually do. You take everything that looks relevant and you put it into the window. The ticket, maybe the linked log, the design document, the file the agent had opened, every tool result so far. Context windows are big now, hundreds of thousands of tokens, and the frontier models run up to a million. So why not? For a short task, this might be fine. It might genuinely work. The trouble shows up exactly in cases like StreamIt, where the task runs long. The term used here is long horizon tasks. Tool output piles up turn after turn. The Docker log alone was huge in my example. The design document is partly stale. And now the model is spending its attention reading thousands of lines of historical notes to answer a question about today's behavior. You did not make the agent smarter by giving it more, you gave it more to be distracted by. And you are paying for every one of those tokens on every single turn, which I will come back to later because it matters more than people think. So the rest of this is really 4 moves for doing better than put it all in. And Lance Martin from LangChain frames context engineering as 4 moves. And I think it is the cleanest model out there. Write, select, compress, and isolate. I'm going to take his 4 moves in the order they tend to bite on a real task. Select, then compress, then write, then isolate, all on the StreamIt bug that I just talked about. The first move is selection. Instead of dumping everything, pull the slice that this turn actually needs. For StreamIt agent, good selection looks like this. When the work is about the encoder restarting, bring in the encoder code and the recent server logs. Do not bring in the score overlay rendering, the YouTube authentication flow, or the parts of the log that are just normal startup noise. This sounds obvious, and it is, until you notice how much of it the harness has to do for you. The agent cannot read the whole repository to decide what is relevant. That would defeat the purpose. So, selection itself has to be cheap and approximate. For example, embeddings over files, ranking by recency and relevance, a search index, descriptions it can scan without loading the full thing. Tools are the clearest example of how this bites. In the talk, Lance points to research showing that tool selection starts to break down as tool set grows. You might have heard about this. He puts the rough edges onto it being in the tens of tools where the first sign of trouble and around 100 for real failures to show up. Those are his approximations on the talk, and the underlying papers test much bigger tool sets. So I would not quote the exact numbers, but you get the gist. The direction is the part that holds, which is past some point, you cannot just hand the model every tool. Mature harnesses retrieve the relevant tools first, the same way you would retrieve relevant documents. If you are building your own harness, this is the first place I would reach for retrieval. Do not register all your tools on every call. Embed their descriptions and pull in only the handful this task needs. The general principle is the harness is constantly choosing a slice. Get the slice right, and the model looks brilliant. Get it wrong, and the model looks careless when it really just never saw the right thing. Here is where selection gets more interesting than just ranking the files. And it is the part of the StreamIt task I find most useful. Remember the ticket linked to an earlier session, the one where we had already dug into the encoder and learned how it behaves? That conversation is not in the current window. It happened days ago in a different session. So how does the agent get at it? That comes down entirely to the harness. I'm going to use Codex, OpenAI CLI agent, and Hermes, the Nous Research agent, as the two anchors here because they make opposite choices and the contrast is clarifying. Codex keeps each session's history to itself. There is no built-in way to load another session's conversation into the current one. That was true for StreamIt work too, which actually ran in Claude Code. And Claude Code isolates sessions the same way. The earlier thread is sitting in a file on a disk, but the agent cannot reach into it unless I go find it or ask the agent to read it explicitly. The selection Codex does do is over the project. It walks agents.md files from your working directory up to the repository root and includes those within like a few byte budget that they have. Hermes, which I also run, makes the opposite choice. It stores every session it has ever run in a SQLite database with full message history and FTS5 full text search over it. And it gives the model a session search tool. So in Hermes, when a ticket points back to last week's work, the agent could pull the thread using some function or tool that it has. It selects just the part of that old conversation that matters and drops it into the current window. That is selection across time, not just across files. Same situation, and whether the agent can recall last week is a harness decision, not a model one. This is exactly the boundary from slide 4. Storing the old session is a memory job, that is primitive 6. Choosing to pull a slice of it back into this turn is context management, this primitive. Hermes gives the model a lever for that. Codex and Claude Code by default do not. One more thing about selection, because it is a bit people skip. Getting the right material into the window is necessary, but it is not sufficient. Where it lands in the window also changes whether the model actually uses it. There is a well-documented finding called lost in the middle, where the model reliably uses the information at the very start and at the very end of a long context and gets unreliable about everything in the middle. So you can select the perfect file, bury it in the middle of a huge window, and you can watch the model act like it was never there. This was some time back and things might have changed, but it is an interesting point to note, and we'll talk about it further. In the StreamIt session, the encoder code was actually stuck in the middle, behind the log, and the model skimmed right past it. Its position more than its presence is what kept it from getting used. Put that same code near the end next to the question, and a model will eventually lean on it. So the selection is two decisions, not one. What goes in and where it sits. Most people think about the first one. The second is free attention you are leaving on the table. Selection gets you a good slice. The problem on a long task is that even a good slice keeps growing. Every turn adds tool output. The StreamIt session was 40 turns and climbing. So the second move is compression. Summarize the running history, trim what is no longer load bearing, replace the raw thousands of lines of log with handful that actually shows the problem. The trick is what you keep. A good compaction is not make it shorter, it is make it shorter without losing the things the next turn needs. When I look at how the better harnesses write their compaction summaries, they tend to preserve the same handful of things. One is goal, the goal we are working towards. Second is the constraints and decisions already locked in. Third is what is done, what is the progress, what is blocked. Then the key files and facts in play. And finally, the next step. That is roughly what you would write a teammate before going on a vacation. Enough that they can pick up the work without rereading the whole thread. For StreamIt agent, a good compaction at turn 40 would say, the goal is fix the choppy low resolution video. We ruled out the YouTube side. The suspect is the encoder tearing down and respawning every time the WebRTC resolution changes. Here are the two files. And the next step is to stop the resolution from collapsing upstream. That is a few hundred tokens standing in for tens of thousands. This is another place Codex and Hermes show their personalities. So let me put them side by side on the StreamIt task. Hermes checks before each turn whether it is getting close to its compression threshold. And when it crosses it, it runs a compression pass and rebuilds its system prompt. The default threshold is set to 50% of the window, and you can push it to about 70 or 80%. One detail worth getting right: When it rebuilds, it does not surgically swap out one section. It rebuilds the whole prompt. The thing that makes this safe for caching is that the stable part, the identity and the tool guidance, is byte for byte the same every time. So it comes back identical. What actually refreshes is the volatile part, the memory snapshot and the session metadata. Codex makes a different bet. Rather than one big compaction event, it enforces hard limits on every piece going in. Their own rules are blunt, and I kind of love them. No single item larger than 10K tokens. Every fragment has a hard cap, and any new item that could cross 1,000 tokens gets flagged for manual review. Skills are budgeted at 2% of the context window. So Codex puts all of this so the context itself would fill slower. And then, of course, they have their limit when it will do similar thing like Hermes as well. The StreamIt log would never get into Codex at the full size in the first place. It would be capped or truncated on the way in. Hermes is more likely to let it in and then compress later when the window gets tight. Neither of the approach is wrong. One trims continuously at the door, and the other does a bigger cleanup when the room fills up. But they are different reliability bets, and it is worth knowing which one your harness is making. Compression has two costs that are easy to forget when you turn it on. The first is that it is lossy by definition. You are throwing away tokens and betting that you kept the right ones. In the StreamIt session, aggressive compaction might flatten the Docker log down to a single comment like video quality is unstable. True, but useless. What it can throw away is the actual smoking gun. Which might be that the delivered resolution oscillated between 1280 by 720 down to 904 by 508, and the encoder restarting hundreds of times. The agent can then spend turns rediscovering what it had already known and summarize it anyway. The second cost is that the compaction in itself is an LLM call. It takes time, it takes token, and if you trigger it too aggressively or too often, you are spending tokens to save tokens and thrashing the agent's momentum every time. So there is a sweet spot, and the compact more is not the same as better. How much say you get over this is itself a harness decision. Some let you move the trigger. Hermes has a compression threshold you set in config, defaulting to about half the window, and it will even fence off the first few and last several messages, so a compaction never touches them. That lines up with the lost in the middle slide that we talked about earlier. The head and tail of the window are high value seats, so they are worth protecting. Codex goes further in one direction. It lets you set the token limit where auto compaction fires, and it lets you swap in your own compaction prompt as well. Sit with that last one for a second. You can hand the harness your own instructions for how to summarize. So the compaction step stops being a black box and becomes something you design. And if you are building your own harness, then that is exactly how I would treat it. The trigger and the compaction prompt are design surfaces, not defaults to inherit. The harness I was in for StreamIt, which was Claude Code, is stricter. I can toggle the auto compaction and give a one-time focus on what to keep, but I cannot move the threshold. So the habit I lean on, no matter the harness, is the one lever that is always mine. Get the things I cannot afford to lose out to the conversation entirely, so a compaction has nothing to delete. If compression is lossy, then the fix for the things you cannot afford to lose is to stop keeping them in the conversation at all. Write them down somewhere outside the window where you can reload them on demand. And that is the third move. And it is the one that changed how I actually run long tasks. For StreamIt agent, writing context out looks like a scratch file. As the agent confirms things, it writes them down to a working note. The suspect is the encoder restart storm. Here is the log signature with the resolution drops. Here is the file where the teardown happens. Here is the fix we already ruled out and why. That file lives on disk. It is not competing for space in the window at all. And when the conversation gets compacted, the note survives untouched because it was never in the conversation to begin with. And Dex Horthy from Human Layer takes this further into a full workflow. And his framing is the clearest I have seen. He has the agent write a research file and a plan file before it writes the code. And this sounds similar to the plan mode, but it is slightly different than that. The research file lists the relevant files and line numbers, so the agent is not searching blindly later. The plan file spells out the changes. Then each implementation step runs in a fresh context window seeded by the plan rather than dragging the whole chat history along. He reports keeping his working context under 40% of the window this way and shipping a lot of code without opening most of the files himself. Those are his numbers from his talk, and they line up with what I have felt on a smaller task. One boundary to keep clean: writing a scratch note for the current task is context management. If that note is meant to outlive the task and inform future runs, now it is memory. Primitive 6. Same file on the disk, different job, depending on whether you are reloading it in the next session or for the next month session or not. Select, compress, and write all operate on one window. The fourth move admits that sometimes one window is the wrong unit, and you should split the work across several. That is isolation. Give a piece of task its own context, let it run, bring back only the result. StreamIt case has an obvious spot for this. Searching that huge Docker log is exactly the kind of thing you do not want your main window to do. So you hand it to a subagent. The subagent's whole job in this case would be to find the restart pattern and the resolution changes in this log. It reads the entire log in its own context, burns whatever tokens it needs, turns the answer to the main agent, and it would say 226 restarts. Here is the resolution collapse sequence, and the main window never sees the other few thousand lines that the subagent had to go through. That is the pattern, and it shows up everywhere once you look. A sandbox code runs and executes something and returns the value, not 10,000 line of print log or std out. A search subagent that returns the answer, not the transcript of how it found it. And we've covered sandboxing as its own primitive and subagents as primitive 8. And this is the context angle on both of them. Isolation is how you keep one agent's mess out of another agent's window. The thing isolation buys you is total capacity. 5 windows can hold more than one. And the thing it costs you is coordination. And the moment you are coordinating windows, you are starting to hand off to orchestration, which is a different primitive and a different deep dive. Here is the thing most context engineering talks skip, and it is the one I would least want you to miss. So far, I've talked about context as if the only question is what is in the window. There is second question that costs real money: in what order and how stable it is. Modern models caches the prefix of your prompt. If the first however many thousand tokens are byte for byte identical to last turn, you do not pay full price to process them again. It is discounted and cheaper and faster. This can be up to 90% discounted. But the moment you change something early in the context, every token after it is now uncached and you pay full price again. This completely changes how you think about the 4 moves. Every time you reselect, re-rank, or compress, you are potentially invalidating the cache. A harness that reshuffles its context every turn can be correct and still slow and expensive. Now let's talk about the two system, Hermes and Codex, and how they design around this. Hermes builds its system prompt once per session and reuses it across every turn. In normal operation, the thing that triggers a rebuild is compression. That is a deliberate choice to keep the cached prefix stable. It even keeps the volatile stuff like late arriving extra memory out of the cache prompt and injects it into the turn's user message instead. So the prefix stays frozen. Codex writes it into their rules in plain language. Build context up incrementally, do not rewrite history, and avoid frequent changes that cause cache misses. So the assembly order is a performance decision, not just a correctness one. That is exactly why Hermes and Codex are built to put the stable things first: identity and instructions and tools, and keep the churny things last. The flip side is a warning for anyone choosing or configuring a harness. If it reshuffles the window every turn to surface the right files, it is quietly blowing the cache and paying full price for the prefix again. That is the cost that hides in the bill rather than the output, which is what makes it easy to miss. So if you are building your own harness, this is one of the first things I would get right before any of the other clever retrieval process. Freeze a stable prefix, keep the identity, tools, and instructions in that frozen prefix, and let only the tail part of the context move from turn to turn. You get that wrong, and every other optimization you add is fighting your own cache. So we have now seen all the pieces on the StreamIt task. So let me put the two harnesses in one view. I held this table until now on purpose. It only makes sense once you have watched both the systems make each move. So the shared pattern here is what I want you to take away more than the specific cells. Both of them do bounded assembly. Both keep a stable cached prefix, and both use progressive disclosure, loading the lightweight description first and the heavy body only when it is needed. Where the differ is the bet. Codex bets on a stricter per item discipline at the door. Hermes bets on a flexible window with reach back across sessions. If my work is mostly inside one repository and one session, the Codex style feels right. If I am living across many sessions and want agent to remember last week's work and last month's work, Hermes style earns its keep. For anyone building their own harness, these two are reference points rather than a menu. Codex shows you discipline at the door, hard caps, a configurable compaction trigger, compaction prompt you control, whereas Hermes shows you a flexible window with reachback like we talked, session search, protected head and tail, one stable prompt per session. Most harnesses I would build land somewhere between the two. And knowing which knob each one reached for makes it that much easier to pick your own. So everything I've described assumes that you can see what is in the window. Most of the time, you cannot. And that is the quiet reason these problems persist. When the StreamIt agent got kind of wonky at turn 40, my first instinct was to, again, rewrite the prompt or change the model. The thing that actually helped was looking at the context. What is in this window right now, and how many tokens is each part eating up? The harnesses that expose this make it much easier. Codex tracks a token budget and can surface window usage. A lot of tools now have some version of a context readout, a way to ask, what am I actually holding? The first time you look at one, it is usually a surprise. Half the window is a log you forgot was there, or 3 copies of some related comments or notes, or a tool result from 20 turns ago that has no business still being present. Of course, models are getting better, but this ties back to the last primitive in the stack, verification and observability. You cannot tune selection, compression, or writing if you are doing it blind. So the habit I would build is simple. Before you start thinking about optimization and fix, look at the window. Most the model got dumb today, things that you hear about everywhere are really the window is a mess issue most of the time. So let me pull the 4 moves into the way I actually run a task on projects like StreamIt, because separately they are techniques and together they become a workflow, right? Um, and what it boils down to is similar to what Dex calls intentional compaction. And so it goes research, then plan, then implement. Right? In the research phase, the agent explores and writes out what it found, the relevant files, the suspect code, all the things that we talked about. That is the right move used early. The output is a research file a human can read, which on the StreamIt bug is a 1-page note instead of a 40-turn transcript. In the plan phase, the agent writes the intended changes to a plan file. Now you review the plan, not some directly diff of code lines. And if the agent misunderstood how the encoder responds, you can catch it here, where it cost 1 comment instead of a day. And in the implement phase, the agent works from the plan in a fresh window. It is not dragging the entire research conversation along. It selected what it needed, wrote the rest to a disk, and kept the window clean. The reason this works is the same reason any of this works. Less junk in the window means more attention on the desk on the task at hand. And every step is just 4 moves applied on purpose instead of by accident. So if you are building your harness, this is worth baking in as a default rather than leaving to the user. A research step and a plan step that each write to disk, then an implement step that starts from the fresh plan. You are encoding good context hygiene into the tool itself instead of hoping someone would run it that way. And it's not, again, you might have heard about this, and people are using it in a way that they will do a lot of research via subagent, which is the right thing to do, but have that subagent write the findings to a file. So the next time the agent can just read that file and it's not even coming into context. So we are back to where we started. The StreamIt agent losing the thread at turn 40. I want to leave you with the question I actually ask now when that happens, because it is more useful than the model is not good enough. When an agent gets dumped mid-task, I walk the 4 moves and ask which one let me down. And then the meta question that sits under all 4. Could I even see what was in the window when it happened? If the answer is no, that is where I start, because I am guessing otherwise. Most of the time, one of those 5 is clearly the culprit. It is either at a select stage where I ask the question, did it ever have the right thing, or was the right thing just buried somewhere? Was it a compress levels issue where did the summary throw away one of the key detail? Is it at the right? Did it lose the work it should have parked and written on disk? Or is it at isolate? Did one giant context drown a subtask that deserved its own window? Right. In the StreamIt session, it was select and compress together. The Docker log took most of the context and buried the signal. And then a hasty compaction deleted the signal entirely. And once I saw that, the fix was the kind I can actually make. Send the log to a subagent and have it write the findings to a file. So neither one can crowd the window or get summarized away. And once the window was clean, the agent got it. It found the real issue that was the upstream to the encoder. And that was not just because the model was different. It was the same model finally looking at the right few hundred tokens where the answer was. The reason I wanted a whole deep dive on this is that the context management is invisible when it works and looks like stupidity when it fails. A great context setup just feels like a sharp agent. A bad one feels like a model got worse overnight, which sends you off tuning the wrong thing. A lot of the time I've noticed when people complained about OpenClaw or Hermes getting worse, or even sometimes agent getting worse, it most likely is the context management issue. Either those agents change something in how they do context management that will show up as it getting worse. So something to keep in mind is watching the change log of what they are changing as part of the agent itself, if any of that is to do with context management. So the shift I would make is in the question you ask. When, again, the agent disappoints you on a long task, do not jump straight to the model. Ask what was in the window and which of the 4 moves you got wrong. Context management is not going to fix the model that genuinely cannot reason about an encoder pipeline. It will not invent knowledge that was never delivered. That is the retriever layer's job. And it will not remember anything between runs on its own. That is what the memory deep dive was about. What it does is narrow, and it carries a lot of weight. It decides what your model is looking at this turn. And on that long task, that decision quietly determines almost everything. I've spent a lot of this video flagging what matters if you are building your own harness. Let me end on the part that is for everyone. Whether you build one or just you use Claude Code or Codex, the habit that pays off most across all 4 moves is to look at what actually gets sent to the model. I mean the real requests, the system prompt, the messages, the tool list in form of the model receives them, rather than the polished transcript in the UI, which, by the way, is a great start. Half of the why did it do that moments have the same answer once you look. Your agents.md was never the payload, skill description was never loaded, or compaction quietly dropped the decision the agent later contradicted. And both Claude Code and Codex will show you a version of what they send if you go looking. And if you want this as a habit rather than a one-off, then tracing tools Things like LangFuse, Langsmith, or any other tool that speaks open telemetry conventions will capture the full prompt, messages, and tools on every call. So you get to see exactly what reached the model and when. It also makes the ecosystem legible. People build plugins, extensions, and skills that quietly do these four moves for you. One compresses your history, one adds a session search, one swaps in a memory file, the other one trims your tool list. Once you read what reaches the model, you can see what each one is actually injecting and whether it helps your workflow or just adds noise. Understanding the primitive is what lets you judge the thing built on top of it. For now, whether you are building a harness or just trying to get more out of one, the question is the same. What is in the window? Which one of the four moves put it there? Hope this was helpful. Thank you.